Alright guys, welcome to this lecture 4 on the RISC-V processor design. We're trying to build RISC-V RV32IM processor core which is able to run CoreMark. And in this lecture, we're going to see what the RV32IM instruction set architecture is. We're going to draft an architecture spec for tiny Vedas as well as a diagram. We're going to experiment with a single cycle CPU. We're going to see that it will have some timing issues that we're going to solve through pipelining, and we're going to start writing the first building block of our core, which is the instruction fetch unit. So let's get into it. So the RV32IM instruction set architecture is divided into mainly two specs, which is the unprivileged and the privileged one. The unprivileged is for bare metal operations, while the privileged adds support for operating systems. We will focus on the unprivileged for now, and you can find the latest ISA spec at that link. So if you access the codebase, download the slides, and click on that link, you will be sent to the landing page they have for all the specs. And the first thing we need to go through is what's the register file for this processor. And this is where we're going to store our microarchitectural state. And you're going to see throughout the spec this xlen value, and this xlen value for every RV32 extension is going to be 32-bit. So it means that we have 32-bit general purpose registers that are named from X0 to X31. There's a catch where X0 is tied to 0, so you cannot write to it, and we'll see later why. Every instruction set architecture defines also an application binary interface. And this application binary interface, what it does is instructs the compiler design team on how to use the different kind of registers. The way the registers are laid out, they're general purpose registers, meaning you can use them however you want, but the compiler needs to know how different registers are used. So the application binary interface defines how registers should be used by the compiler. And for example, if we take X1, it's mapped to RA, and it's used by the compiler to store the return address. So when you call a function, the return address of that function call is stored in the RA register. And the same thing goes, for example, for the function arguments, the saved register, the temporary register, so on and so forth. So we're gonna see assembly code written with X0 to X31, and we're gonna see assembly code written with the application binary interface. We just need to remember and look back at this table to see the mapping between the different kind of naming. So we saw the register file. Now we'll see the program counter. And the program counter is the register that holds the memory address of the next instruction to be a 32-bit register as well. And we'll see what kind of operations we must be able to perform on this register on the next few lectures. But in general, you can imagine that we need to be able to increment the program counter to get the next instruction. We need to be able to load the program counter to make a jump in the program, and we need to be able to load with offset, so to add or subtract an offset from current program counter to be able to execute if and else statements. So this is a rough idea of what we need to be able to do with this program counter. And now we land on the juicy part, which is the instruction encoding. Instructions are encoding into 32-bit words in RISC-V in general. This has nothing to do with the fact that this is a RV32-bit architecture. We have 32-bit instructions regardless of the particular spec that we have, meaning that even if we had a 64-bit processor, the instruction would have been 32-bit as well. The instruction encoding is extremely regular. This means that it's going to be easy for us to develop decode tables for this processor. And you can see here, RISC-V, at least the basic instruction set extension, defines 6 different instruction set, defines 6 different instruction encoding. So for example, let's take the R instruction encoding. This means that the operands are both fetched by the register file and the destination is the register file itself. And every operation adds an opcode, and then as part of that opcode family, we differentiate between the different kind of operation with these funct3 and funct7 fields. For example, the R-type instruction, which can be an add, and you can find this online, you can find it in the code base. We will have a very handy document that will list all the instructions that we need to implement with what they do and what is their encoding. So for example, from that document, if we take the add operation, is R is the register file. What it takes is the content of the register file pointed by RS1, the content of the register file pointed by RS2, and adds that and puts that in the content of the register file at RD, which is all encoding in the instruction. So for example, bits 11 down to 7 of the instruction tell us what is the address of RD, and the same thing for RS1 and RS2. As you can see, we have 5 bits for the address of the register file for the 3 operands. Why it's only 5 bits, it's not 6 and it's not 4, because we have 3 registers. And if you remember from the previous lecture, you know that the address width is the logarithm base 2 of how many entries I have in the register file or in the memory or whatever I'm trying. This is like a zoom out version of that document, and you can see that here we have all the encodings, and here it spells out what the opcode is, what the function 3 is, what the function 7, if the encoding has that, is. And with this document, we're gonna build the decode tables for our processor, but this is gonna be part of next lecture. We now have enough information to start laying out a very loose architecture spec for our processor. And we will assume that our processor will handle one instruction at a time, and we'll see what this means in the context of pipelining, because it gets a little confusing, but it's not going to be confusing by the end of this lecture. Each instruction has at most 2 source operands and 1 destination operand. This has some implications on our register file. In particular, it means that our register file will have 2 read ports and 1 write port. And moving forward, we will logically partition the design into 4 stages. The instruction fetch unit, the instruction decode unit numbered 0, that understands what the instruction does and asks for the operands to the register file, which will be in instruction decode unit number 1. And then finally, we will execute the instruction to the instruction execute unit, where we will execute it and commit, so write back the results to the microarchitectural state, which in this case is the register file. This is what we're gonna need in order to get the instructions. We're gonna need a program counter that assumes a byte addressable word aligned instruction memory. We're gonna see what this thing means in the next lecture, where we're gonna build the top level test bench with those memories in. We will call this the instruction closely coupled memory, ICCM. Why closely coupled? Because we can access this memory in 1 clock cycle. And we will see how to initialize this ICCM in our top level system Verilog test bench in order to initialize the memory with the program, the instructions that we want to execute. What about the data memory? We will assume a byte addressable word aligned, and we will see how this is going to cause some interesting issues for which we're going to need a queue. And we'll call it a data closely coupled instruction memory, where the access latency is still 1 clock cycle. This is a very simplified memory architecture, but at least it gets us going. So this is what a very initial, very brief architecture diagram what's going to look like. We're going to refine and update this diagram as we go, but this is what the 4 stages will look like. IFU, IDU 0, IDU 1, EXU, the write back to the register file, the program counter here that asks for the instruction to the ICCM. And for now, we're going to have an ALU and an ALSU to ask for data. Here in the IDU 0 stage sits the register file. And that's pretty much as far as we will go in today's lecture. We're missing what? A control unit to update the program counter. We're missing quite a few things. We'll get to that as we progress throughout this course. Now, if we focus on a little thought experiment on how this thing should work in terms of a single cycle CPU, how it should work is that the IFU unit gets the first instruction from a CCM, which is a clocked access. Remember, the read operation on a memory is clocked. IDU 0 gets the instruction and decodes it. IDU 1 gets the operands from the register file. Remember that the read operation on a register file is unclocked. The EXU executes the instruction and writes the result to the register file, which is now clocked. The whole operation happens in 1 clock cycle because we have the launch flop at the ICCM and the arrival flop at the register file. From a timing diagram perspective, each takes half of the clock cycle. And the performance now depends on how can we drive that clock cycle frequency, how fast can we go in terms of getting those instructions from the ICCM and pushing it down our architecture and getting the results inside the register file. Let's start talking about the timing characteristics of flops and registers, because this is something we haven't seen in the previous lecture, but it's something that we have to check. And we have 3 main times that we need to take into account. One is the setup time, and it's the time that the data D must be valid before clock transition. So this is one requirement that we haven't seen in the previous lecture. But from a physical perspective, we have to make sure that the D signal that feeds a flop is stable a little time before the rising clock edge comes in. And this little time that we have to wait is called setup time. And it depends on the fabrication process. If we're doing a ASIC implementation, it depends on the FPGA characteristics if we're doing FPGA implementation. And it really depends on the physical architecture that we are dealing with. So this is extremely important. The setup time, as we will see, will determine how fast can our processor go. A hold time is the time that the data D must be valid after clock transition. Remember, if you remember from the architecture of a flop, you saw that we had basically 2 latches in a what is called a master-slave configuration. We have to allow some time for the first latch to propagate the data through the second latch. And this time that we have to wait is called a hold time. So after the clock transition, we have to maintain the D signal stable. Otherwise, the signal gets corrupted at the output of the. So the hold time violations are the ones that get fixed first by the synthesizer, because otherwise the circuit is not operable at any frequency. While the setup time violation is a matter of being too fast, meaning that our circuit cannot go as fast as we want to. And we're going to see in the next slide why is that. Then we have a propagation delay, which is basically how long it takes after the rising edge of the clock comes in for the Q signal to change. So for the Q signal to follow the D signal. Here is the timing diagram, and here is the setup time, this is the hold time, and we assume here we have a small skew in the clock, but if you imagine this thing was like a sharp edge, this is the delay from clock to output. Let's focus on the setup timing violation. And the setup time violation happens when the signal takes too long to propagate and the next block may sample the signal too late. So what is the constraint? We are in this situation where we have a launch flop and a capture flop separated by some combinational logic or combinatorial logic. So what is the requirement for this combinational logic in between the two flops in terms of propagation delay to make sure that R2, so register 2, flop 2, correctly samples the output of the combinational logic when the clock cycle comes in? So the clock period, the requirement for the clock period, which is the inverse of the frequency, is that it must give enough time for the first flop to launch the signal. So we have to wait a clock to Q time. Then the signal needs to be able to propagate through the combinational logic, so T logic, and we have to give enough time for the signal to be stable before a setup time, before the second flop can sample it. So if we put everything together, the clock period must be greater or equal than the maximum of delay plus logic plus T setup time. This is called the time enclosure problem, and a single CPU would be dominated by T logic, because if you remember, we have to go through 4 stages of logic, including the execution unit, which is like dramatically slow. So we cannot make the logic arbitrarily faster. So what can we do in order to achieve the 3 gigahertz of frequency that we have today? We need to break down the logic to multiple steps. And the way we do this is by pipelining. So we can break the combinatorial logic into smaller, faster blocks. So suppose that we have this combinational logic that takes, 500 nanoseconds of propagation delay to execute. What we can do is we can split this thing in half into 2 blocks of 250 nanoseconds, 250 nanoseconds, and put a register in between. So now the T logic, it's not 500 nanoseconds, but is 250, meaning that if we neglect the constant here, the setup time and delay, we can make our circuit twice as fast in terms of clock frequency. Okay. So ideally, if we repeat this thing on arbitrary amount of time, we can introduce n pipeline stages, and if we can balance it perfectly, we can run at a clock frequency of n times the original clock frequency. What it means to balance the pipeline perfectly means that each stage of the pipeline will have the same propagation delay. And this optimum solution is called the Amdahl law, and it applies to any parallel system. And we will see that pipelining is a parallel. So this is what we're going to assume. We're going to assume that we have an output register at each of our 4 stages. So IFU has its own output register, IDU 0 and IDU 1 have their own output register, and the EXU as its own output register, and the register file, of course, as its output register. So seemingly we increase the latency of an instruction going in, because now it's not anymore a single cycle CPU. Now we have a latency of n clock cycles, and in particular we have a latency of 5 clock cycles, because it's the original first clock cycle plus the 4 register that we added at the end of each stage. But this is not the case, and this is why it's called a pipeline. What happens to a pipe when you fill it up with water? The moment you turn the faucet on, you have to wait a little while before the water starts flowing, But once the water starts flowing, you get a continuous stream of water at the end of the pipe. So this is the same thing that happens here. We can now overlap the operations of different instructions at different stage, meaning that while an operation is in EXU, the IDU stage can be decoding the next instruction, the IFU can be fetching the next instruction, and once the pipeline is full, so each stage is processing its own instruction, we still have one instructions coming out per clock cycle, but at n times the frequency. So you saw here that we dramatically increase not the latency, but we increased the throughput of our system. And the throughput here is measured on how many instructions we can process per second. So if we want to visualize what we just said, we are putting registers in between pieces of combinatorial logic. And if we want to see it on a time-wise, if we plot it on a timeline, we can see that instruction 1 goes through stage A, B, and C. When instruction 1 moves to stage B, instruction 2 comes inside the pipeline at stage A, and when they both move, instruction 1 to C and instruction 2 to B, instruction 3 enters the pipeline and goes into stage A in this case. You can see here we have a 3-stage pipeline and we are executing instruction 1, 2, and 3 all in parallel, not concurrently, but in parallel because they are inside our pipeline. So this is why it was confusing at the beginning when we were saying, oh, it executes an instructions at a time, but it is pipeline. So a more correct way of stating that would be that we have one instruction coming out of the pipeline each clock cycle. Of course, it's not all roses and flowers. Pipelining comes with his fair share of issues. Data hazards, control hazards, structural hazards, and we're going to deal with all of those things in the coming lectures. We can now start looking at the code base and start developing what is the instruction fetch unit with all the assumptions that we have, knowing that for sure we're going to need to revisit that by the end of the course. But what the instruction fetch unit does is it generates the program counter, it gets the instruction from the ICCM and updates the program counter to get the next instruction. So let's head over the code base. And the first thing I want to walk you through is the behavioral library. And this behavioral library, which is under RTL lib, it's a collection of small units, big units, whatever we're going to need to implement our units. So for example, here we have the D flip-flop, the D flip-flop with reset, and the D flip-flop with reset and enable that we saw in our previous. The way those flops are coded is slightly different that we saw in our lecture, but it's not going to change their behavior. The nice thing about everything that you saw here in the behavioral library is that it's being silicon tested, meaning that there are chips out there that have been coded using this library. And you can see that we have all the flops that we saw, which are parameterized by width, so meaning that they can become registers. And then we have the program counter. And if we look at what the program counter does, it has a clock and reset, because of course it's a sequential element. It has a reset vector, which is the value that this program counter is going to be initialized to. And this is important because it will initialize the address of the first instruction. And we can set this thing arbitrarily. For now, we're going to see what the value is, how we're going to deal with it. We're going to have the control signals, such as load and increment, the data signals with the PC in for the load operation and the PC out for all the other ones. So you can see here that if we assert the reset, we load the program counter with the reset vector. Otherwise, if we are loading the program counter, we load whatever PC in is. Otherwise, we are incrementing the program counter with the increment amount, which is 4. So why are we incremented by 4? If you remember from the slide, the instruction memory is byte addressable. What it means that each different address identifies a different byte in the memory. And what this means is that given the fact that each instruction is 32-bit, so 4 bytes, we have to increment by 4 to get the next instruction in memory. So this is why you see here that the increment amount is 4. If we go quickly on the global system Verilog header file, you can see that we have all the constants that we need, including xlen, to build our processor. We're going to go over these constants when we will start building on the next lecture the top level and the top level test bench. But here now let's focus on the instruction fetch unit. And we have a clock reset, which is, of course, we have it. Then we have a reset vector. And what this reset vector does is the initialize value for the program counter. We have the memory interface for the instructions. And then we have the interface to the next stage of the pipeline, which is the instruction decode. So if we look at the instantiation of the program counter, we have the clock reset and reset vector that goes straight into the interface of the top level design. We are coded to 0 the load operation. We are coded to 1 the increment operation, since we don't have yet a control unit. And I wrote here to be changed later because this is going to change. And we wired to 0 the program counter in, since we don't have a load operation right now. And the program counter out goes straight to the instruction memory address. And after 1 clock cycle, we're going to get the data, so the next instruction, and a valid signal from the memory saying, okay, this is valid. This is a valid instruction from the memory. We're going to flop it, and we're going to pipe it down to the next stage. So this is a D flip-flop with a reset with width of instruction len plus 1, because we are piping down also this instruction memory valid. So we are concatenating the 2 signals to create a bigger one. And these brackets are how we concatenate signals in system Verilog. And that's pretty much all there is to the instruction fetch unit for now. This unit is going to go under major rework throughout the course. But for now, this is what we have. So we can wrap up this lecture here. We're going to see on the next lecture how we can build a top level for this design, meaning how can we start building our core and instantiate the instruction fetch unit and connect it to the instruction decode unit, put it inside a top level test bench with the instruction memory, the data memory, and start seeing something flowing between all those components. Next lecture focus is going to be also decode tables. That's where things will start to get messy, but we're going to have fun doing it. So tune in for the next lecture.